So welcome back. I hope everybody's enjoyed the coffee or snack or something. And we're going to move now to a very interesting section, which will be focused more about data query and data delivery services. And at the end, we're going to see some interesting example from Alex showing basically some part of analysis pipeline, the realistic example. So first speaker will be Mason. Mason, are you here?
Yes.
Yeah, okay, great. So please share your screen and
This one.
Thanks.
Yeah, okay. So I can yeah, go ahead and get started. So again, you can find the binder link in the GitHub repository on the agenda, but it should also be in the Open Data Proffitt Analysis Grand Challenge repository. So this would be in this is the FuncADL demo, and the notebook is called demo, like the last one, like the one I had earlier. Okay, yes, so I'll be talking about FuncADL, or Functional Analysis Description Language. So this is another case similar to my earlier talk with uproot, awkward, and vector. I'm again kind of presenting a fundamental building block that other things can be built on top of, that like service X that you'll hear about. These are things that use FuncADL. So the first, again, I'll talk about the motivation for FuncADL and what is it. So there are two important concepts that kind of influence FuncADL. So the first is query languages in general. So database management systems have been around for quite a while now, and they address, among many issues, two things that I mentioned here. So the first is data independence. So this is the idea that the physical schema of data, in other words, how the data is actually stored, what the format is, where that file is, and even the storage medium itself, if it's a hard drive or SSD or living in RAM, is independent from the logical schema, what is actually stored. So like in the case of what we saw earlier, floating point numbers representing the transverse momentum in GeV of each muon in each event in a particular run in CMS in 2012. So because there's this intrinsic separation, this kind of very abstract separation between the physical schema and the logical schema, how this data is stored and what is stored, the way that you specify or query the data should not be tied to any of the details of the physical schema, how the data is actually stored. Sorry if there's a noise in the background. These lights in this office make noise sometimes. So in other words, the query that you write to in order to select some data from a database should look exactly the same in this database model, whether that data is in a root file on, say, the worldwide LHC computing grid, or in a totally different format, Parquet, stored in a totally different place, like just on your local drives. And so this separation between the physical and logical schema has not been the case for most HEP software, at least up until fairly recently, and it's still the case for a lot. So sometimes you have to totally switch frameworks or even programming languages to deal with a different format or a different location based on where the file is. And then the other concept that I'm just highlighting from databases is the idea of data redundancy. So this redundancy is multiple independent copies of the same data existing. And so this happens all the time in high energy physics, mostly due to the fact that there are file formats that exist at different levels of detail. So you can think of like full AODs versus derived AODs in Atlas, or mini AOD versus nano AOD in CMS. And there's also the raw data, which is usually only ever on tape. So it's the same data. It's the same data from the same events copied many times. And there's the size of that changes based on the level of detail, but it's the same events. So the storage requirements, in this case, if you have more copies of the same data, just the storage requirements increase linearly. It may be a slight different scale factor based on how detailed it is. Nano AOD is going to be smaller than mini AOD, but it's still the more copies of it you have to make, the size of that on disk will increase linearly. And also importantly, the more independent copies that exist of data, the more complex it is to make sure that everything is synchronized. In other words, that all these copies are actually the same, and there wasn't some copy didn't get modified or didn't get copied correctly. So in a good database system, the data may be physically backed up with many copies, like redundant disks, but there's only ever one logical version of the data. So when you execute a query, you're not creating a brand new copy of the data that then has to be maintained separate from the original. You just get a view of the data as stored in the central database. And query languages are an important aspect of database management to address these two issues that I mentioned before. So like SQL is by far the most common query language that pretty much everyone is familiar with. And then the other influential concept for FuncEDL is the functional part, the functional programming or functional programming languages. And so again, I just highlight a few concepts from functional programming that are very important and useful for physics analysis. And so the first is that it's declarative. So this is effectively the code equivalent of data independence. So this is the case where what the code does can and should be separated from how the system is actually executing it. So instead of explicitly telling the computer to do something like loop over each event, and then within that event loop over each muon, and then for each muon access some property or properties like the PT, you can just declare what you actually want. So in this case, the PT of all muons. And then the programming that's executing this query is free to get the information however it wants. It's not specified as part of the interface how the data is actually retrieved and processed, as long as it provides the right answer. So it's kind of, you can think of it like a compiler. In this case, the execution engine for the query can be designed to fully optimize the reading from disk or network transfers and computations that are necessary to perform the query. But a physicist who is just running an analysis and doesn't have a computer science PhD in databases doesn't need to worry about things like caching or advanced CPU instructions. And even if they are a specialist in these things, you just it reduces the cognitive load and reduces the amount of code that you have to write, because you just can separate these optimizations from the writing the selections of data, and you still get the benefit of these advantages, these advanced optimizations. And then also with functional programming, pure functional languages have no side effects. So a side effect is something like modifying a global variable, and because it changes the global state. So if there's no state, then a function will always return the same value regardless of where it is in the code, given the same inputs, the same arguments. So it's only the function is only the function output is only dependent on the explicit arguments of the function. So operations performed by a function are totally independent from any other function that it doesn't call. And then finally, functional programming is lazy as in lazy execution. So a query itself is a well-defined object, contains instructions or a function for what to do with some data. And so you can pass around and compose queries before you even have access potentially to the data that it will run on. And so a query isn't executed until it's necessary to do so. And so these concepts from query languages and functional languages lead to more modular code. It makes the code, it separates the code from the format and data location, and it insulates different parts of the code itself from other parts of the code. So FuncEDL is a functional data query language using Python as a host language, and it's based on this LINQ, language integrated query, which is a set of features that are built into the language C#. Okay, so so that was the first half or so, and then the rest I'll show how to actually start using FuncEDL. So again, I'll be using matplotlib. Actually, let me just clear. So, I keep forgetting how to clear the outputs, but I'll just do it this way. So yeah, again, I'll be using matplotlib, and so here I'm importing. So FuncEDL has several different backends. So FuncEDL is kind of the interface, the interface where you actually write queries. So we'll write queries again that will run on a data set, and though that query syntax will be the same regardless of what is actually the backend that's running the query. But so there are several different backends that can run on different file formats, but expect the same query syntax to drive them. So in this case, I'm using an uproot backend. So I'm saying from FuncEDL uproot or uproot data set. So this is explicitly saying that the files, the queries that I write here will be executed using an uproot backend that was written to interpret FuncEDL queries. And then I'm using, this is a different data set from the one that I was using earlier, but it's similar. It's another open data thing. And again, I have a small subset available in the repository, but then the link to the full file is somewhere below. Right, so we just say uproot data set and then give it, in this case, the file name. It can also be a URL or xrd URL, and the tree name here, which actually is optional. It should work without saying events, but it's a nano AOD like format, so events is the name of the tree. So now this data set is ready. It's ds equals uproot data set. So now I'm going to start writing queries. And so the way this is structured is, so at times, like intermittently, I'll introduce new query operators and start building up, so adding query operators to kind of a little inventory that we can use to write queries, and then show how those operators apply to just some basic tasks that come from this repository here that are designed to benchmark the functionality of analysis description languages. So, okay, then now getting into, really getting into the language here, the most important thing to understand about FuncEDL is that everything is treated as a sequence. So like an array is a sequence of elements, and in pretty much all cases, at least at the highest level, where if we're talking about like a T-tree, a T-tree is a sequence of events. So here, so you can think of a T-tree as an array with different branches. Those are the fields, but each entry each row is one event. So the data set object, like I said, is just a sequence of event objects. And an event object is a record in the awkward language, or a dictionary containing all of the properties of the event. And these values are like primitive values like int or float, or are sequences themselves, like the arrays of muon pt that we saw earlier. So almost all functional operators expect to act on a sequence of some form, which can be a sequence of sequences of sequences, and so on. So the most important operator is select. So select transforms each element of a sequence according to a predicate function that's given. And then the output, the return value, is the sequence that is formed by running this function on each element of the sequence. So it's basically a map, like in the Python built-in function map. So, and for each one of these operators, I show like a very kind of like toy example on just a basic little sequence. So here, if the sequence is 1, 2, 3, just you can think of it as a list or a tuple or array or whatever. It's just a sequence of 3 numbers. If I say dot select and then give it this predicate function, so here the input is the argument, the x, and the output is x plus 1. So this is saying transform each element in the sequence such that it becomes x plus 1. So the input is a sequence and the output is a sequence. So it runs this function on each element. The output sequence contains the elements that result from running the function on the elements of the input sequence. So 1 goes to 2, 2 goes to 3, 3 goes to 4. So this is the only operator that you need for the first task, which is in this case just get the missing et miss of all events. And so this is in a branch that's in the nanoAD files. So here I'm assigning the query to a value, and I'm saying ds.select, and then so this data set is a sequence of events, and then for each event that goes in, I want to get out event.metpt, which is the et miss. So I can, assuming I've executed all the cells before, I can just execute that, and it immediately returns. It didn't take any time, even for a huge data set. It doesn't take any time because of this delayed execution. The value isn't calculated, the query isn't actually run until you explicitly ask in some way, like adding dot value to the query. So then if I execute this, it's still very fast because there's this small file, but it takes slightly longer than the almost immediate return of just assigning a query. So now the result is stored in this missing et variable. And so I can execute that, and I can see it's an awkward array, 1 dimension. It's got 10,000 numbers in here. So this is just the missing et for each of it. And then we can plot it just for fun to get an idea of what the distribution looks like. Okay, so that's the first one. Another similar operator is SelectMini, which first does the exact same thing as select, but then there's an additional step. So it assumes that each element in the original sequence gets mapped to a sequence itself. And then after performing this mapping, it concatenates all of the resulting sequences. So if we have this example again, the 1, 2, 3 sequence, if we run a SelectMini where we map each element to a list of 2 elements with x minus 1 and x plus 1, then you can see what happens is so it'll map 1 to 0 and 2, and then it'll map 2 to 1 and 3, map 3 to 2 and 4, and then it takes all of those like sub results and just concatenates them to get 0, 2, 1, 3, 2, 4. So it makes all of these sequences, and you can think of it as flattening the second dimension here. And so this is exactly what I said here. And often this SelectMany is used when the initial elements were already sequences. So like in this case, where you have a jagged array, where the first row has 1, 2, and then the second row has 3. Here, the SelectMany is just this identity function, so it's just passing through each row. So it's passing through the subsequence, the sequence that's inside of the sequence, and then it'll just pass all of those through and then just concatenate them. So it just flattens if this function in here is the identity operator. So it just gets rid of that jagged structure. It just flattens to a 1D array. So if we need to deal with an object collection within each event, so something like jets, then we often will use SelectMany if we don't care about the delineations between events. So if we want to get the PT of all jets and not worry about which events they're in, we can use SelectMany. So here, say ds.SelectMany, and then event gets mapped to event.jetpt, and then all of the jetpt arrays for each event will get concatenated. So I can execute this, and then we see that it's just a 1D array of jetpts. And so that's, and you can see if we did a select instead of a SelectMany, we would still have this jagged structure. And so you could get from this to the previous result, but then you just have to do like an ak.flatten or ak.ravel to flatten that jaggedness. And then again, we can plot it. Okay, this is that jetpt. Another very important operator is where. So this is for filtering. So this one's pretty straightforward. So it again takes a predicate function that should return a Boolean value. So like in this case, if we want to get the elements that are greater than 0, say that's x is the input and the output is x greater than 0. So if we apply this to a sequence that has negative elements, they'll get filtered out. So it just, the result of this operation just ends up being 1, 3. It's removed the -2. And okay, and then zip is again important, especially for collections within events. So like we saw earlier, the muons had several different branches associated with them. So like PT, eta, phi, and mass. Often we want to collect all the properties for a single muon together so that it looks like a single element, a single object. And that's what zip does. So there's this example with numbers, but it's not, this looks very much like the Python built-in zip function, where it basically does a transpose of this, in this case, a rectangular array. So it takes a sequence of 1, 3, 5 and 2, 4, 6, and it matches up the first elements and the second elements and third elements of these two sequences. So it picks out 1, 2, and then 3, 4, and then 5, 6. And so the extension from the Python built-in zip is that you can also do this with dictionaries. And so in this case, if you have 2 dictionaries with A as a key for this sequence and B as a key for this sequence, the output will be an array of dictionaries where it picks out these again, the first elements and the second elements and the third elements of each and matches them up. So in awkward language, turns a record of arrays into an array of records. And so a task like the next one, plot the PT of jets with an absolute value of eta less than 1, requires this kind of zip thing, because we want to filter based on a different branch from what the output should be. So we only want PT to be the output, but the filtering needs to be done by eta. So you can do this. So I can zip together PT and eta so that the PT and eta of each jet are like joined together so that they're connected, and then they become a single object. And then I can filter. Now I can say dot where and filter by the absolute value of this zipped object where the eta absolute value of eta is less than 1. And then once I've done the filtering, then I can just pick out the PT and then execute that. And then that will give me the PT of all of the jets passing this filter. And then again, we can plot it. Another operator is count, which is a very basic one. It doesn't require any function input. It just counts the number of elements in the sequence. So like for this sequence with 3 elements, if you run .count on it, it will give you 3. And so this can be used for something like this, where you need to make a cut based on how many jets there are with passing a certain cut. So here it's jets or events that have at least 2 jets with PT greater than 40 GeV. So here I'm going to filter on events. So I say where, and then within this event filter, I pick out jet PT, filter the jet PT values that are greater than 40, and then count how many of them there are. And if there's greater than or equal to 2 in this event, then the event will pass this filter, and then you can select the met. And then that gives the met values, and the distribution of met is different from the earlier one we did when we didn't have any filtering. Let's see. So choose is another one that provides like a very useful thing that's not easily expressible with the other functions, and that's dealing with combinatorics, combination that you have in analyses. So choose produces all combinations of a given inside a given sequence with a particular number of elements. So it's the name comes from like n choose k for combinations, where you have this. So here we have this sequence of 3 elements, and if you do .choose 2, it's saying provide all combinations of 2 unique elements from this sequence. So you get 1 2 1 3 and 2 3. So you can do this to get like pairs of jets or pairs of leptons. So, and then the other thing that's been added to this funky ideal interface is this 2-4 momenta, which is something that can be run on if you have all of these properties, PT, eta, phi, and mass, and they've been zipped together, like I showed before, then so that means that the 4 vectors, the properties of the 4 vectors basically exist and they're connected, but they're not actually a 4 momentum object yet. And so 2-4 momenta just performs that. So it turns it into a vector so that you can actually run vector operations on it. So it tells FunckyDL to interpret this these objects as 4 vectors.
Mason, I'm sorry, we just probably have like a couple of minutes left, so just in case, think about it. Yeah.
No, I don't have to get to the most important things to get probably to this one here. So then this is just an example of doing that. So here I zip together all of the properties of muons, turn it into a collection of 4 momenta, and then so this is looking at muon pairs. So it's looking at like taking opposite charge muon pairs and looking at the invariant mass. So you zip together the 4 momentum and the charge, choose pairs, which is this choose 2, and then you look for where these charges are different within this pair. You can perform the 4 momentum operations right here. So add these 2 4 vectors together, get the mass, and then filter based on that invariant mass. And then you could count it, and then you can also filter the events, and then again select the met for these events. And then, okay, so I won't go through the very last one, but I'll just say another couple. Not all of the operators are in this notebook. I just picked some important representative ones, but there are things like sorting, where you use this order by operator. You can sort by a particular key. So this again takes a function that tells you how to sort the elements. And then there's there are things like first and last, which is it's just more readable synonyms for using numbered subscripts. So like taking the first element. Okay, and then so that's the end. I'll just look at the questions here. So how does choose method scale with length of sequence? Well, exactly, it uses AK dot combinations. So it will scale in the same way that function does. And how does Funky work on the hood? Yeah, so this is the last questions. Are queries compiled, and is the implementation sensitive to whether a query is columnar friendly? Well, the interface forces you to use a columnar, like the interface. That's part of the advantage of FunkEDL, is that it kind of restricts you to some extent to this narrow set of tools, which makes it much easier to optimize these things in a columnar way. And for the first part, yeah, so I explicitly didn't talk about FunkEDL, how it works on the hood, because there are all these different backends. So it depends on the backend that's being used. So there's an XAOD backend, for example, where your query is converted into actual XAOD-based C++ code and then compiled and then run on the file. For the case of uproot, of course, there's no compilation. It just gets run. It generates Python code that uses uproot and awkward to run these queries. So it depends on the backend, but you can always write more backends to use different libraries or run on different types of files.
Thank you so much, Mason. It was really amazing talk, and I as usual, I enjoy your talks. Yeah. So I hope, in case if you have any other questions to Mason, probably you can stay a couple more minutes and check. Maybe somebody will